Stanford University.
Okay, can you hear me? Yeah, so unfortunately I don't have those. At the time I was explaining to Sally, I said I wish I had my slides here, but I managed to do it without the slides. But I actually don't have those slides here today because I'm here to talk about something slightly different. For those of you who keep on saying to me, you must be tired because it's a long way to come, I've just spent the last 8 days on the beach in Maui, so I feel pretty relaxed. But ever since I arrived here, the time Nazi here, Sonny, has had me on a schedule that is incredible. It's just, there's no, so the next time you do it, give someone a break in the middle of it. Because even after this, when you all go for your social, I have to go to another meeting apparently. I'm not even going to get a free beer. So look, thanks for inviting me. I'll be very, very brief about this. Is the research group I lead. It essentially came out of industry. It's definitely an industry and applied research group. It's not we do pretty basic work, all right, but it's pretty much a research-driven organization. So I'll go through my slides very quickly. Before I do, have you done your homework? So I sent some papers in beforehand. Stanford put them up on the website. So I assume you've all read the background material, correct? Well, I met a lot of people today, in fairness, who had, because there's a lot of synergies. I tried to change the slides during the middle of the day to sort of adapt them to what people said, but I didn't get an awful lot of time to do that. But was any of it relevant to you? So I think the key question here is in my talk is, how many of you are engineers? Oh, wow. Economists? Oh, wow, it's mainly engineers. That's good. But you'll find that this area is broader than engineering. It's got some economics in it. It's got some social issues in it. So I'll try and keep it fairly general. And hopefully by the end of it, you'll say that I learned something from it. So this is how I'm going to do it. I'm going to just, I was asked to give a sort of a layman's introduction. So I'll do this little introductory piece about supply-demand balance and flexibility, what it means. I'll give some sample systems. There's some real systems out there that are flexible. There's some real systems out there that are not so flexible. I'll go through the consequences of that. I'll try and quantify flexibility. Flexibility is something people talk about, but can you put a number on it? And then unlocking flexibility. How do you make systems more flexible? There's short-term issues and there's longer-term issues. I'll look at some of the negative consequences of flexibility. And then to look to the future. A lot of people today actually, in fairness, one of the last questions they had for me was, what do you think the future looks like? I gave a radio interview this afternoon, and I was asked what the future looks like. I'll try and talk something about that. If anyone wants to interrupt and ask any questions during it, please do. I'd rather ask questions during the slides than at the end, but whenever you want to ask a question, please do. So supply-demand balance. So I know a lot of you are engineers, but not too many are electrical power engineers. So I'll just try to explain very quickly what supply-demand balance it is and why it's so important, and the issue of flexibility. So grid frequency control, it's an analogy, but it'll do for the purposes of this talk. This is a tank of water. This is supply. This is demand. This is the load profile. It's actually a load profile from Ireland. This is the generation. So generation goes in and meets the demand, but there's a small amount of storage here. And the frequency can be taken to be the level of the water. So if too much water goes in, the frequency goes up. If too much water goes out, the frequency goes down. And if the frequency deviates too much, like it did in Italy. This is the Italian blackout in 2003. The most recent blackout in India was another blackout, but it wasn't quite as dramatic as this with regard to the frequency issue. This is probably still the best blackout example of why frequency control is so important. I won't go into the huge amount of detail, but basically what happened was the Italian system got disconnected from the main European grid across Switzerland. The Swiss blamed the Italians blamed the Swiss. I'll leave it up to you to decide who it was. Like I said, I'll always buy a Swiss watch, not an Italian one. But you can see here that this is the frequency in the system, 50 hertz, and it plummeted. And the reason it plummeted was because this one here is the total imbalance. So once the system's in balance, in this case, the imbalance was negative. There was too little generation, too much load, and therefore the frequency plummeted. And at this point here, that was the Vatican, right? Blackout, total Italy gone. If you look at it, in terms of time, this took about 3 minutes, okay? Now, just to give it some context as well, the amount of water that's in this tank, does anyone want to guess how long that water would last if the supply stopped? Approximately. Approximately 10 seconds. So there's not a huge amount of storage in the system. There's a very small amount. And at the very end of the talk, I will talk more about the issue that myself and Sally talked about. So the amount of storage here is tiny. So this really has to maintain supply-demand balance almost instantly. And if it doesn't, the system blacks out. And the reason flexibility is so important is because this thing is moving. Yeah, the load is moving from minute to minute, hour to hour. So you must maintain this supply-demand balance act. You must do it almost instantly. And therefore, you're going to have a flexible system to do it. So without introducing renewables, the system has to be flexible anyway. So it's not a case that renewables meant that we have to have a flexible system. The system has to be flexible no matter what. It's just a matter that when renewables come on board, it probably has to be a bit more flexible than it was before. So what is flexibility? These slides will go up on the web. I'll leave a PDF. You can read them yourself. There's a definition for one of my PhD students. This is a paper he published. This is another definition. But let's read this one. Flexibility is the ability of the system to deploy its resources to respond to changes in net load, where the net load is the remaining system demand not served by variable generation. The reason is that we'd like to accept all the variable generations we can because it's free. Now, it's not capital cost free, but once it's built, it's free. So you want to take it all. Once you want to take it all and serve all the load, it's the net load that matters. And the net load, this is a slide from my colleague in NREL, Michael Milligan. If you look at the load here, so the load is in red, and the net load is in blue, because you'll try and accept all the wind you can. If you notice that I have to meet this supply-demand balance, the red one, but if you look at the blue one, it's a bit more dramatic. The steeper ramps and those lower turndowns. So yes, I need the system to be flexible anyway, but with variable renewables, I need it to be even more flexible because it adds to the variability of the system. That's wind. If I put solar on it, it's pretty much the same, very similar impacts. I'll mainly stress wind because in Ireland, we have an awful lot of wind installed. We don't have an awful lot of sunshine, so we don't have an awful lot of PV. We do have some PV, but very little. Ireland's resource would be mainly wind, but in Southern California, it would be PV. The flexibility paradigm, I don't want to spend too long on this slide because the main reason I use it, it's a slide developed by us a few years ago to try and sort of give an idea of what are all the components of flexibility and some of the terminology. So the sources, well, let's talk about the sinks. The things that cause it to be needed is the load is changing. Solar and wind come in to make it a little bit worse. The things that are the sources of it, the things that can respond. The generation itself can respond. Conventional generation can respond. Storage can respond. I can get interconnection. I get megawatts from somewhere else. Variable generation itself can be a source of flexibility. The demand side could increase or decrease. So these are all the sources. And these are what we call the matchmakers. These are the things that put it together. This is the reason. These are components, and this is the system tying it together. So transmission networks ties it together, fuel storage, forecasting, markets, gate closure, grid codes, unit commitment. I'll talk about a lot of these as I go through the slides. But there's operations issues, institutional. I'll make a big distinction between physical issues and then institutional issues. Like physical issues is building something, institutional issues is changing the rules, whatever. And then there's sort of gray areas in between them. But you can see that there's markets are involved, economics, institutional issues, operational issues, planning, physics, sources, sinks. There's many different aspects of this problem, okay? And you put them all together and say, I want to make the system more flexible. And someone says, oh, well, how do I do that? Well, all of these have abilities to make it more flexible. And I'll try, in a matter of the next 35 minutes, give you an idea how. So some sample systems. My wife is a yoga teacher. And that's me trying to touch my toes. So some systems are more flexible than others. And I'll just try and illustrate this by this. If you look at wind curtailment estimates in the United States, and curtailment, in other words, if I dump wind, it's a very good negative metric for flexibility. If I am throwing free, incrementally free wind or solar away and not using it, it's an indication the system is inflexible. So in fact, the single best metric that I know of for flexibility, let me just, sorry, go back a bit. Yeah, is not actually a metric that I will give you here now and do some maths and analysis on. It's actually look at the system and how much wind are you wasting. It's a good negative metric. If you can accept all the wind, it means you're flexible. So the first and foremost metric that you should use is how much curtailment you have. These are statistics from the US and various systems compiled by my colleague Charlie Smith. I think as far as I know, he actually got them off Ryan Weiser in LBL, but Charlie's name is down there, but I think it's Ryan Weiser's data. But anyway, he went through it and he did some statistics here about curtailment in percentages. Let's look at ERCOT. ERCOT would have the most wind of any system in the United States. 8.5% of it in 2011 was wasted, okay? So let's go on to, I'm sorry, I think the analogy is good, spilt beer, okay? So wind power in Ireland. Let's look at Ireland. So this is the Irish power system. This data is about a year old. You can see here that this is the load, this is wind. You can see that Ireland sometimes hit, first of all, 50% instantaneous penetration level. Sometimes the Irish system hits 50% of its energy from wind. But you can see that we have very high penetration levels of wind. But the most important slide is the next one. This is wind growth in Ireland over the last number of years, and these are some statistics. So in 2000, I was away in Hawaii for the last week, so I didn't have a chance to do the 2012 statistics, but I'll do them next week. Anyway, for 103 days in 2011, wind went over 40% of demand. In November 26, 38% of the total demand was served by wind. In 2011, there was no storage available in the system at all, none. The pumped hydro station was out on maintenance for the entire year. There was limited interconnection. We are a synchronous power system in our own right. This is the interconnector that's functioning, was functioning at the time. This is a new one. This one wasn't commissioned yet, and this one actually broke during the year. So for a large period of time, during the winter, when the wind was highest, we were a complete and total island with no storage. Curtailed wind energy in 2011 was 2.3%, or 1/3 of ERCOT's. Yeah? 16% of energy in 2011 was in wind, twice ERCOT's. So in terms of performance metrics, flexibility-wise, we performed 6 times better than them. That's a bit of a simplification, but nonetheless. We had more wind than they had. We curtailed 1/3 less. We have twice as much wind and curtailed 1/3 less. So on that metric, we're 6 times more flexible than Texas. Yeah? And then, but I think the key thing here is 65% of our other electricity generation is from gas. And that is one of the aspects that makes us flexible. The other aspect that makes us flexible is this. This is in a report I did for the Australian energy market operator. They wanted to know about their system and to learn from other systems around the world. And they asked me to put together sort of international perspectives on wind and wind integration. So that's New South Wales and that's South Australia. But as it turned out, I also did ERCOT in Ireland. So let's look at it. Let's look at Ireland first. This is 24 hours in a day. It's the average wind and load at every hour of the day for an entire year. So it's every hour of the day averaged over a whole year. And you can see that our load pattern is this classic diurnal pattern. You know, we go to bed at night, we get up during the day. And you can see that our wind has a slightly diurnal pattern as well. It tends to be windier in Ireland during the day than at night. Look at it in Texas. Well, ERCOT is essentially Texas, not quite, but essentially. So I could do many more graphs and show you many more, but this is the one that I'll just stick on. Our wind is much more correlated with our load, making it much easier to maintain supply-demand balance. That's essentially what the point is. So we have a lot of gas, and our wind is very complementary to our load. Texas, unfortunately, has wind during the wrong times of the year and during the wrong times of the day. We tend to have wind during the right times of the year and the right times of the day. So I call them dance partners. Actually, New South Wales is extraordinary. It's incredible. And South Australia, of course, is very, very similar to ERCOT. So that's the first thing, is that every system is different. Just go to China. I'm an international person. If anything else, US, Europe, can't leave China out of it. So you look at China, these are their curtailment rates in various provinces, but this is key. 2011 wind curtailment was 17%. That was of the stuff that was connected, because 75% of it wasn't even connected to the grid. It's what they called wind art. Yeah? But the key question is about China is that load growth is so fast that may well be just a legacy issue. As China, the load grows, the new thermal plant can be made. So as they build out more and more, they will build it to be flexible. And I would suspect that's what's going to happen in China. Whereas if you take load growth in Europe and the USA, our load is not growing that fast, so we have to deal with the system we have. So quantifying flexibility, how do you measure it? Who wants and needs to know? I mean, many people who want to know a number about flexibility are policymakers. No policymakers in the audience, correct? Good. Policymakers are simple people. They want a simple number. Is it 7 mark? Is it 6? Is it 5? And policymakers have been striving to say, how flexible is that system? And I say, well, it has to do with the correlation. It has to do with and they say, hold on a minute, I want a number. So that's one of the drivers. People like a simple number. They like a metric. So they want to say out of 10, how flexible is your system? So maybe ERCOT's a 4 and Ireland's a 7 or something like that. That's one of the reasons. So these are policymaker type people. This is your CPUC. Have I got them most up to date, have I? Yeah? Is that there? This is this California Public... Sorry? Yeah. So these people probably have some interest in flexibility. These system operators definitely have a real issue in it, but in fairness to them, they know it can't be a simple metric. These people, the thermal generators, will have an interest in flexibility. The markets have a because the markets are such that they sort of hear, the system's not flexible. It's not a good investment environment for wind because if it's not flexible, I'll be dumping wind. So the markets say, that system's not very flexible and I'm not giving you money to build your wind plant. So they have an interest in it too. And obviously the developers of the renewable plants themselves. So there's a lot of people have an interest in these metrics. There's different time frames, and I haven't placed these in any strategic way because the important point is that real-time operation happens here. Supply-demand balance must be met instantly at that instant in time. There's a little bit of swash in it, but not much. 10 seconds, in fact, 10 seconds is the total amount of storage in it. We're talking about seconds to deal with this. But you have this sort of planning is years out, operations is closer to sort of weeks out on real-time operation. So planning and operations, in both here you have to make sure the system, 5 years out, 10 years out, you must make sure that you have the plant available to serve the load in 2015 or whatever it is. And you must make sure, so things done here impact things here, things done here impact things here, things done here impact things here. Different time frames, very important to remember. Here's the operational time frame, here's the planning time frame. I'm going to try to split them into two. One is sort of long-term investment issues, the others are short-term operational issues. The reasons why you might want to put metrics on these things is this is a curve drawn. I've attributed to UWE, which is Utility Wind Industry Group, Charlie Smith, but I think it's actually Michael Milligan's slide, but I can't be 100% sure, but it's a slide that many of us use. We've said low cost, high cost, and in our opinion, and we have research needed. If someone really wants to know how these exactly sit, you can't say, this is more flexible than that if you don't have a cost number with it too. But you can't say how flexible something is till you can measure it. So this is really just saying research needed to determine the shape of the flexibility supply curve. So that's where a lot of work's been done at the moment. But in our opinion, markets are just a set of rules. Flexible generation, traditional storage, wind curtailment. Wind curtailment is a form of flexibility. It's that negative form of flexibility I was talking about. And then storage, because storage as a technology tends to be very expensive. Now we're not saying this is exactly how it looks, but this is roughly how it looks. A complete integration study. You could do a complete integration study, which is the things that, this is NREL's study in the Western Wind Integration Study. This is a California study. You could do a complete integration study. You could do all this if you wanted to. But people are really interested in here. They want to say, I don't want to pay $5 million for this study. I want a number quickly. And that's the type of things that we're trying to work and help with people. This comes from IEA Task 25, which is an International Energy Agency task on wind integration. And we're working on a report to trying to give some guidance to people how to do integration studies. But how we did it, so this is a piece of work that we did, is that we went and said, okay, this thing over here was the capacity value. So let me explain that. If somebody asks me how much capacity, if I install a new generator of any type, shape or size, be it a nuclear generator, wind, how much additional load can I serve and maintain the same level of reliability? If I install one more generation plant in California, I'm probably going to be able to serve a certain amount of extra load across the entire year and maintain the same level of reliability. And the question is, how much is that? That's what's known as the capacity value. And in thermal plant, it's usually pretty high because largely speaking, thermal plant will be on pretty much whenever you want them. In wind's case or solar, it's less because it's not a controllable resource. I'm not here to talk about the details of that. But we then said, well, can you develop a similar, because these are well understood techniques, very robust statistically, very well understood, and they are a genuine number. We can give a number. So we said, can we adapt this technique here to this here? And the answer is, you can, but the problem with it is, this number can be calculated without any preconceived ideas about how to operate the system. This number here cannot be calculated without including the operations of the system. So it's a much more complicated way to do it. So we took the idea, we'll use the knowledge about this and we will adapt it to work out a flexibility metric. And look, the paper's there and the slides have a long list of references at the end, and it's one of the papers that you all read for your homework, correct? So you all know about it. And this is, again, details in this paper. We're trying to just show how this metric that we developed was similar to the so-called ELCC, which is the way that capacity values are calculated. And here's the metric, some of the results. Now, flexibility is a horizon thing. If someone said, so this is the insufficient ramping rate expectation. It's the expectation that I will not be able to ramp, to change. So it's not a sort of an expectation of not being able to serve load, it's an expectation of not being able to change fast enough to serve the load as the load changes. And it's obviously going to be different over different time horizons, yeah? because, if you have 1 second to react or 5 hours to react, it's different. And what you find is, I'll go through the different color codes in a minute, but what you find is that up and up it goes, and then down and down it goes. And the reason why it falls off there is, in this particular example, we have combined cycle gas turbines that take 4 hours to start. So it's sort of saying if something changes here, you'll have a hell of a lot of capacity available within 4 hours. And that's indicative of that fall. So you can see that as the time horizon goes out, the errors in terms of forecasting wind get bigger and bigger. So your insufficient ramping rate expectation increases, but all of a sudden you've reached 4 hours, I can start a combined cycle gas turbine, I'm fine. The reason the difference between the different ones, and it highlights the issue, this is not a metric that is independent of how you operate the system. So this is showing you in a case where you carry a lot of reserve. If you carry a lot of reserve, you have an awful lot of extra capacity online available to ramp if you need it, but it costs more. So this costs more than this one. And this one shows you the impact of outages. So it's a very complicated metric. Unfortunately, it's not a single number because we showed it to the policymakers. They said, hold on a minute, it's a graph, it's two-dimensional. And look at that. And it's also got these parameterizations on it. So it's still not simple enough for them. But that's as simple as we're going to make it for them. They can pay one of those big consultancy firms to make it simpler for them. There's more metrics. I won't go into them. This is one metric by a colleague of mine, Daniel Kirsten, who's up in the University of Washington. And there's various other metrics being developed at the moment. But pretty much they're the only 3 papers in the world at the moment about metrics in flexibility. So unlocking flexibility. So so I'm going to talk short-term operational strategies. Now, I just put this slide in, and I can, Sally, where's her husband? I'm going to blame him. Where's he? Terry?
My fault.
Yeah, so if I get into trouble for this slide, his fault. Because he was the second person today who talked about this. I just slotted this in. Beware of the hammer and nail tribe. You get these people who always say, your problem, or my hammer, your nail. Everybody. And it came up 2 or 3 times today. Terry was the last person to bring it up to me. So before we get on to the solutions, let me go in the following one. My iPhone is in my pocket, but there is a tendency for the IT business in particular, and this is Stanford, this is Silicon Valley, this is the home of the IT business. There's a tendency for the IT business to say, electricity, we know all about that, no problems. There's many differences, but let me put it this way. How many times has your call failed? Once a day, twice a day? How many times have you been without electricity? They're totally different things, okay? Electrical engineer, power engineers run a much more reliable system than any telecommunications system alive. Not only that, but how many systems, this business here is driven by teenage girls wanting to send text messages. It's a totally different business, yeah? We produce electricity to save lives, yeah? So we're a serious business. The other thing about its scale, this is a HVDC converter. This is the size of a human being. The iPhone fits in your hand. This electronics and this electronics is fundamentally the same, but just at a different scale. This is shipping bits, this is shipping terawatt hours. 2 different products, 2 different markets, totally different, yeah?
But to be fair, though, you have to...
I'm not going to be fair.
Well, okay, you're an engineer. So you do have to credit the regular old phone system with extreme reliability.
Oh, yeah.
Okay, that's the POTS.
Yeah.
Who uses that anymore?
You don't have one because you know what you just said about your cell phone.
But most people don't.
But I'm not here to beat up in the IT business, because the IT business, the electricity business are definitely coming together. There's a lot of synergies to go on. But just be careful. Everyone will claim that their solution is the one you need. Okay. So before I go through all these solutions, just be careful of that. Did I get it, Terry? I think we got away with that. Okay. So aggregation and win the larger balancing areas. So one of the solutions to all this is to make the system bigger. Because if you make the system, this is data from Germany. It appears in an IPCC report. Ryan Weiser was the main author. I'm in there somewhere as well. And you can see if you look at it, single turbine, a group of turbines, all of Germany. If you aggregate things together, this sort of variability becomes smoothed out. That makes it much easier. If you look at the ramps that you require, if you make a bigger system, the variability that you would deal with is less. The ramps you have to deal with less, the requirement for flexibility is less. If you look at California, this is I'm not exactly sure where I got this, but this is California here. This is the Western Interconnection United States. This shows all the balancing areas. So let me be very clear about this. This is one electrical system, okay? The Irish grid is one system, this is one system. It's one synchronous power system, but they maintain supply-demand balance in each of these areas. Now, from a physical point of view, an engineering point of view, supply-demand balance is maintained on a system-wide basis, that's it. But administratively and operationally, they maintain it on an individual. So they're essentially balancing, they're balancing the system area by area on a system that from a physics and reliability point of view should really be balanced on the whole. Now there are reasons for this and I'm not going to go into them. I'm not saying it's a foolish thing to do. I'm just saying they're sort of making life harder for them. They're balancing a smaller footprint. If you were to allow it to sort of balance all together, this aggregation issue comes to your benefit. There's other downsides as well. So I'm not saying this is sort of a quick fix, but making the system bigger is a good idea. Wind forecasts, if you go and do some forecasting, if you know what's going to happen, that horizon issue is very important. If I know I need to get another combined cycle gas turbine on in 2 hours' time, I'll turn it on 2 hours' time beforehand. So if I have good forecasts, I'll be able to do something about it. More regular dispatch. If I revisit the system and replan it more regularly, because the forecast error gets bigger as time goes out, the horizon. Forecast of wind in the next second is almost perfect. In the next hour, it's pretty good. For 1 day ahead, it's worse. So if I redispatch my system more regularly, if I make it bigger in terms of a footprint, if I use good forecasting, I can maintain supply-demand balance fairly easy. The amount of flexibility I need is not that large. Take a drink of water. So this is another slide from my colleague, Michael Milligan in NREL. And basically he says bigger is better, faster is better. So they did a study on the Western Interconnection United States showing that if you take a small balancing area, medium-sized balancing area, large balancing area, and if you take these different times, these are the dispatch times, and the lockdown time is the time that the forecast has got. So it's a three-dimensional graph. But basically, from top to bottom, it shows you need less regulation. Regulation is an amount of generation that you need, let's say on standby, to maintain supply-demand balance. So basically, out here you need a lot more than you do down here, showing you that make the system faster, the market's faster, make it bigger, use the forecast most up to date, you need less flexibility. It goes from here to here, roughly what? Yeah, 1/10 the amount of regulation is required. So you need less flexibility. So this system requirement for flexibility is far less than this one. So they're the sort of the operational issues. People are looking at new flexible products. This is a report from Cal ISO about introducing a flexible ramping product. This is some work done in Ireland. Again, they're looking for a ramping product. So people are looking at introducing new market products to introduce ramping into the power system. One of the problems, I'm not going to go into a huge amount of detail, is how do you design a market that people will actually make money out of this? And it's a non-trivial question. But let me get on to the investment. Unlike in flexibility from a planning point of view, I'll put in brackets investment. It's not quite, if I'm going to build something new, what would it be? So first and foremost, interconnection and transmission. This is the eastern half of the United States. This is a conceptual plan to build a large-scale high voltage overlay across the eastern part of the United States. Reason is cheap wind here, expensive electricity here. Build transport system, deliver renewables to New York City. The economics of it are very good. The politics of it are not so good. You think your budget is difficult, you try and build transmission from one state across another state and they're not getting benefit out of it is also the problems. So that's a political issue. In Europe, there's talk about building offshore grids to harness offshore wind. And in China, there's huge transmission projects. So both in Europe, United States, and China, there's plans. They're on paper. In China, they're not on paper. They're building them. But that's because they draw a line from A to B and they build it. But the most flexible thing you can do of any power system, because remember, if you make it bigger, you aggregate everything. The most flexible thing of all in the world is transmission, by far. And although it's a funny slide, it's a serious slide. Build transmission is the single most important thing. This slide is Dave Corbis from NREL. I'll blame him if there's some copyright issues. If you look at Denmark, Denmark has a huge amount of wind. I don't know if you can see this very clearly, but basically the green line and the purple line coincide. One is wind, one is export. Denmark exports its wind to the rest of Europe, or put another way, Europe integrates its wind. Denmark has in Jutland here around about 3 gigawatts of wind. it has 3.2 gigawatts approximately of interconnection. It's got more interconnection than wind. We have 2 gigawatts of wind and 400 megawatts of interconnection, so we can't export it. So transmission is the key, and Denmark is a classic case of proving it. But here's an interesting research question. What does transmission do to flexibility metrics? You think this was, I can assure you this is a very difficult thing to work out. You know, this is in this paper which you've all studied carefully. But you put transmission into it, it makes a complete mess of it, okay? It's interesting, transmission actually has an interesting, most people would say transmission should improve the situation, but maybe not, because it's got to do with the operation issue. So transmission constraints should schedule more units online when there's congestion, okay? More part-loaded units means more flexibility online, okay? Congestion will limit the export capacity, reducing flexibility. So the problem is, putting more transmission may actually have a negative impact depending on how you operate the system. So the point is, make your capital investment in transmission, but make sure your operational methodologies coincide with that. So you can do one good thing, but you can do another bad thing. So it's an interesting question about how, and we're working on this at the moment, how to include transmission into the flexibility calculation. Well, here you go. Can thermal power plants skip? In other words, can thermal generation be very flexible? The answer is open cycle gas turbines are very flexible. Combined cycle gas turbines are not as flexible, but they're reasonably flexible. Coal plant are inflexible, and nuclear plant are even more inflexible. This is from the National Nuclear Energy Agency or something like that. But anyway, the simple fact of the matter is that some thermal plant are more flexible than others. Now, I do not want to be dragged into this debate because I'm not a thermal power plant person, right? My understanding is open cycle gas turbines is the thing sitting on the wing of the Boeing 747. That is what it is. It's essentially a gas turbine hanging off a wing. That thing can start pretty quick and do all sorts of things. You're going to fly a plane in it. They're very flexible. Nuclear plant, I think you'll accept, are pretty inflexible. Okay, so but there are people. I'll go on to this slide here very quickly, who claim that looking for flexibility, more flexibility in coal than gas. So there are some people who claim that coal may be more flexible than gas, but I don't want to be dragged into that. I think there's more to that than meets the eye. But here you go. Here's GE's website. They actually have their website. Look, http://ge-flexibility.com. Yeah, GE are selling gas turbines on the basis of flexibility because they know it's a key asset or it's a key attribute that people want in the future. So efficient, flexible, and reliable technology. And natural gas is replacing coal at the moment in the US. So I'm not going to be, I found this on the website. It says source departments. My source is not Department of Energy. My source is the internet, and they said their source is Department of Energy. But I think most people will accept that coal has been displaced by gas at the moment. Whether these numbers are exactly correct or not, and that's because of shale gas. So it's interesting. As we introduce more efficient units, because remember, gas are more efficient, then it may also be more flexible. So you may actually get this flexibility without doing anything. And you'll get CO2 reductions as well, which is probably pretty good. So storage. I just want to talk about storage very quickly, and several people today have asked me about storage. This is a piece of work we did a few years ago. I won't dwell on it too long, but this is 6 gigawatts of wind installed in Ireland. This is 40% of our energy on average. This is 80% of our energy on average. This is curtailment. There's 4 plots. The top 2 plots and the bottom 2 plots are the ones I really want to concentrate on. Because the top 2 plots, the bottom 2 plots indicate perfect forecasting. They say, I'll explain the difference between the two of them in a minute, but top 2, bottom 2. Bottom 2, perfect forecasting. If I could forecast the wind perfectly, which you can't, I perfectly accept that, how much curtailment would you have? And you can see it's in the order of 2, 3, 4%. That's at 80% wind. That's a huge amount of it. Like, that's colossal, right? So you're saying if you can get forecasting perfect, that's the benefit. Because remember, curtailment is negative flexibility if you want. These two here range from 16 to 12%. This is state-of-the-art forecasting, okay? And you can see the difference between them is of the order of 10%, yeah? If you look at the difference between these two, between here and here, one is with storage, this is the one with storage, this is the one without, this is with storage, and this is the one without. The difference between the two storage cases is the order of 5% and 1%. The basic point I'm trying to make is that storage is capital cost very expensive, yeah? You may be better off investing in forecasting technology because it's software, it's cheaper, it's more flexible, and storage tends to be very expensive. So I'm not saying storage is a bad thing, I'm simply saying if you compare one with the other, you may find that forecasting may be better. Okay, Psych, how am I doing for time?
Yeah, you're doing well.
Sunny's there. She hasn't got her red flag out.
Yeah, another 10 minutes or so.
I'll be done in less than that. Cycling thermal plants. So one of the problems then is that people say, well, hold on a minute. You're going to take these thermal power plants and you're going to move them up and down, start them more often because of wind. That has a cost, and it does have a cost. We did some work, and I mean, it's not surprising that as you put more renewables, these are renewables, wind energy penetration, these are showing utilization rates and hours of ramping. And there's no doubt about it, more wind, more thermal cycling, more starts. And that does have a cost. If you go talk to a good mechanical engineer who knows about metal, they know that if you heat it up and cool it down and start and stop it, it essentially wears out in some way. Again, I'm not an expert in it, but a lot of mechanical engineers will tell you this is true. And then the designers of these baseload power plants say, hey, it was designed to be turned on in 1940 and turned off in 2010. Turning on and off is not a good idea. It has costs associated with it. So there's no doubt about it has costs associated with it. This is a huge interest at the moment. And NREL have just completed a study in it, a second phase of their Western Winds integration study to try and quantify this issue, and it's still an ongoing piece of work. But we looked at it and we said, okay, we don't know the exact cost because nobody does. Consultants will always tell you it's very expensive. Why? Well, because they want, well, we would do some consultancy, which it's very expensive to start and stop these units. You need to know more about it. So I think they're probably overinflating the costs. There's certainly costs, but what they are, nobody really knows. Thermal power plants will go to the CPUC and say, oh, very expensive to start and stop. You better give us more money. So they're biased. So nobody really knows what the real costs are. You'll only know what the real costs are in 2030 when you close it and someone gets the books of the plant and does some calculations on it. That's 30 years from now. So we used numbers that came from a reasonably reputable source, and what we did was we operated a system, or we simulated it over a 3-year period of time. And what we did was we said every time you start a unit, the next time you start it, it costs more, because that's essentially mimicking long-term cycling costs. And in other words, we were saying if the operator was to account for this long-term cost, was to account for it in the short term. So in other words, it's a long-term cost. Cycling is a long-term cost, but to try and account for it in the short-term operations of the power system, you find that what happens is that these units are with the costs added, and these units are without them. Okay, and what you find is that what basically happens is that over time, what was a very flexible open cycle plant, essentially from an economic point of view, becomes inflexible because the cost of keeping on starting it get higher and higher, and it might be better to start a more inflexible plant. And what happens is the two things start to converge. And that's interesting enough, and you can see you see the wave pattern there. That has to do with the fact that this is 3 years, which is seen as a seasonal pattern. But I suppose the most important thing from this audience point of view is this. This shows you the total system cost savings potential. Now this is 1,000, so the base is down here. If you model those costs long term and if you did not. And it's indicating that there might be 20% to be saved. But this is based on numbers that I don't know if they're true. But all I'm saying is that if you account for the long-term cycling costs in a short-term operational basis, there might be an awful lot of money to be saved. But look, it's an academic paper at the moment. People are interested in it, but the numbers that feed the study are almost arbitrary because nobody really knows what the costs are. But what it does tell you is, in a short term, if you operate in a certain way, there's potential for long-term savings. And then multi-mode operation of combined cycle gas turbines. Combined cycle gas turbines are open cycle and combined cycle, so they can run in an open cycle manner, which is more flexible. And in many markets, they're only allowed to run in one way. If you allow them to run as open cycle gas turbines, that's allowing more flexibility in the system. And we've done some work on that. The problem is the results are ambiguous. The reason they're ambiguous has to do with the fact that as you put more wind in the system, there's more combined cycle gas turbines available. Their economics are cheaper, and therefore what they do is they displace the open cycle gas turbines. So it's a systems problem. It's unresolved. I'll let you read the paper. Future grid. So the last thing I want to talk about then is, so what does the future look like? This is a very nice diagram that I took from the IEEE Power and Energy magazine. This particular article I thought was particularly nice. It's showing that the system's changing. There's more HVDC in the system, more high voltage DC, more DC in general. And if you just go back to Ireland at the moment currently has, around about 15 or 16, 17, 18%. I think this year might be 18 or 19% of wind on the system. And its target for 2020 is up here. It's the largest target of any of these systems. Great Britain, continental Europe, Scandinavia, Malta, and I'm sure it's larger than any target in the United States as well. And this is non-synchronous generation. This is not generation that's synchronously connected. It's connected by power electronics. One of the big questions is, if you put power electronic devices on a system, a synchronous power system is a synchronous power system because it's got synchronous generation. If I replace that with asynchronous generation, what you currently have is a synchronous power system with some asynchronous generation. What you'll have at very high penetration levels is an asynchronous power system with some synchronous generation. The entire physics changes. So we looked at it, in particular EirGrid, with system operator in Ireland. And this is wind, this is load. This green box shows you where we currently operate in. This is our load going from about 2.5 gigawatts to a little bit over 6. This is our current wind. This study was 2010 or whatever, okay? These diagonal type lines show you the instantaneous penetration level. This red box is out of bounds. You've got more energy than you have load, so you can't go there. This shows you 25% instantaneous penetration. This shows you 50% instantaneous penetration. This shows you 75%. If you go back to the very first slide I showed you, you'll see at the 50% penetration it actually dips because the Irish operator will not go above 50%. The reason is that they find in here, so this is real data, this is study data. Green means it's okay. This means it's not okay. And what happens is in steady state the system is fine, but if there's a fault in the system, it has got no inertia or very little inertia. The system basically doesn't recover from the fault. So in steady state it's fine, but dynamically it's not fine. And once you go from 75 to 100%, so we reckon this yellow area you can get around by being clever. We reckon this area you can't. So the really fundamental questions about flexibility is technical flexibility. In other words, not sort of, I think the megawatt balance issue is pretty easy actually. I think this issue is the megawatt balance issue on a microsecond basis is far from easy, and that's the real technical issue. And just finally then, so with GE, SSE and EirGrid, we're looking at a GE technology called wind inertia to try and tackle this problem, and we've published some academic papers on it, but we're actually going to do a demonstration in 2013 with their technology to try and get us essentially, to try and get from there to there. At the moment, we're curtailing wind here. We want to be able to not curtail wind until there, because this is costing a lot of money. Now, at the moment, we don't often hit this, but as we put more and more wind, we'll have more and more times where we curtail it. That costs money. We want to make the system more flexible, and how to do that is not through megawatt balance on a sort of hour-to-hour basis. It's megawatt balance on a microsecond basis that you need it. So finally, demand can be flexible. So people talk about the demand side. These are two papers by colleagues of mine in Denmark, and these are in Germany, and they look at EVs and heat is very flexible. So demand side is a very flexible resource. Demand side management is very popular. Everybody's talking about it. One of the things is, though, if you look at it from a business point of view, the amount of money on the table is very small, and I call it the 2 pints of beer syndrome. So you have a situation where someone says, I want to take control of your load forever, make it flexible, and in return, the amount of money that's totally available in terms of the service turns out to be approximately 2 pints of beer a month. In other words, there's not enough money on the table to make it work. So it's not a technology issue. It's a pure out and out, is it worth it issue, okay? And if you go to any of the studies that are around there, the amount of money on the table for people, EVs, heat load, the amount of money that people can make out of this is so infinitesimally small. 2 pints of beer is not a lot. That in fact, there's not enough money on the table. So it's not a sort of a technology issue. It's a business model issue. I mean, if Shmuel Oren up in Berkeley has said that what he should do is you don't give them the 2 pints of beer every month. You put them into a $10 million lottery every month, and then everyone will play. So maybe there's ways of doing this. And maybe centralized planning is a way of doing it. Maybe in China, they might just say everyone shall participate in demand side management. So it can be very flexible, but it's far from clear that it's an economically sensible thing. Well, it's not. It's a good thing to do, but will you or I give control of our load over to someone else for 2 pints of beer? Maybe the answer is yes, maybe the answer is no. So the last thing I want to talk about then, if you put all that together, so you now got heat load and you got transport and you got markets, the whole thing then comes down to sort of a big energy systems integration question, because I've just put transport, heat, to marry to electricity, I've got gas. So the future of energy systems is really about the emergence between electricity, gas, thermal load, data, of course. So been nice to the IT business now. It's a very important part of it. But just be careful. They're not everything. They're part of it. And it's across different sizes of systems, across regional systems for transmission, smaller systems. So energy systems integration, I think, is a very important sort of If you want to solve these problems, solve them at scale, solve them across all the domains and put them all together. And the last thing then, so just to get international convergence, we worked with NREL in the US, EPRI, which are close by here in Palo Alto. I've got a PhD student who's going to do a secondment to China's state grid, which I think is pretty interesting. It's pretty interesting for him anyway. And these are students that we co-supervise from Oxford and DTU. So there's an awful lot of people involved in this area who are internationally based. This is Eric Ela, who's a PhD student of mine, who's an NREL employee. So it's becoming a much more international and diversified area. So here's the conclusions. Flexibility in grids is important to help integrate renewables. Every system is different. Metrics allow us to quantify it, but the key metric, I think, is reduced curtailment. That's real, it's tangible. How flexible is your system? I curtail 20%, not so flexible. So the real issue is an outcome measure, not maybe a sort of an academic measure. There's operational and planning aspects. Operational aspects are probably easier to do because they're changes in rules, the ways you do things. Planning issues are much more long-term and much more expensive, and also probably much more important when it comes to higher penetration levels as well. There's many sources of flexibility. I suppose if I had the time before I changed the slide, I would say beware of the hammer and nail people, because everyone says that their one's the cheapest. But the challenge to design markets, because if you look at the demand side issues, how do you get people to participate? If you try and encourage flexibility in electricity markets, it's not that easy to do. Switch from coal to natural gas may be the key for the US. You may actually be getting a much more flexible system without doing anything about it, purely because of gas. Future grids have research challenges in technical flexibility. So if you go to very high penetration levels, this supply-demand balance issue that to me is, most people can understand it in terms of, you know, the water and all the rest of it, but most people can't understand it in terms of fast dynamics of power systems. That's for specialists only. That's the key sort of challenge of the future. And the sort of whole thing of putting it all together is very important. You've got data, electricity, gas, thermal, transport. They all start to merge together. And it's an international collaboration is critical. Was this of any relevance to you? Was it? Okay, thank you. And there's the acknowledgement slide.
Okay, so I will help you with questions. So anyway, we have time for questions now, and students first. So any students who have questions? Yeah, over here.
The argument is that if you dump a bunch of money into natural gas, you actually have an incentive to make the rest of the grid more flexible, because natural gas can respond quickly enough to handle the frequency grids and the renewables. So is it wiser to like think more long term right now and look at upgrades in the grid and focus less on natural gas? I mean, there seems to be no incentive.
Yeah, but okay, I'm a power system engineer. I'm agnostic to all technologies. I assure you of that. I'm not here to save the planet. I can't be, because that's for other people to do. Because power system engineers have to be agnostic to every technology that comes along. So your question is from the point of view of CO2, correct? I'm in favor of reducing CO2, don't get me wrong. I think you can't wait. I mean, you know, people are using electricity every day. Renewables are growing slowly. Gas is a better thing to burn than coal. Some people call gas a transition fuel. They call it a transition fuel. And
So, I mean, I see it possibly as a transition fuel too, but they're saying that if you only have so much money you can invest, right? And if you build all these natural gas plants, then you have now, you don't have that money anymore to put into a more flexible grid, right? And you don't, with natural gas online, you don't need a more flexible grid because natural gas responds quickly. But in the long term, if you run out of natural gas, I mean, you would have wasted that money.
I think by the time you run out of natural gas, the gas plant will probably be out of date as well. I'm not trying to avoid your question. I know what you're trying to say. You're trying to say that maybe we're better off going straight for a pure renewable future, correct? It's going to be very difficult to get there very quickly. It's going to be very difficult. It's a long-term issue. I think it's much better to burn the gas and displace the coal and have a flexible power system and get there than it is to either A, incredibly expensive, unreliable system. I don't think people will go with that. I mean, it's not an ideal solution from the point of view of CO2, but it's better than burning coal. Twice as better, as far as I know. The single biggest decline in CO2 in the world, in any industry, in any country in the world, was last year in the United States. I think it dropped by 4 or 5 or 6%. And in fact, in Europe, I think it might have went up. And Sally can tell you why.
Okay, how about over there?
So there's a debate in California right now where the utilities are arguing that distributed resources add a lot of costs to the grid that are affecting all ratepayers. So solar customers are taking benefits that all ratepayers have to pay for. The other side of the argument is that distributed solar have benefits on the whole grid that are not being captured. So I was wondering if you could weigh in on that debate.
Okay, the one, some people ask me questions like how much does it cost to integrate 1 megawatt hour wind or 1 megawatt hour solar? The answer is it's impossible to tell. It's like baking a cake and then asking someone to extract all the ingredients. Well, you might be able to do it, but it's pretty impossible. It's very difficult to allocate costs to this. It's a system. And a system altogether, it's very difficult to calculate pure integration costs. So the arguments are right on both sides. PV on the roofs of houses in Southern California has negatives on the system. It also has positives on the system. If you ask anyone to do an accounting exercise on it, I can assure you any methodology they use, I can rubbish. I can absolutely destroy it because they have to make assumptions. The only way of knowing what the true cost is to have one system with it and the exact same system without it and run the two systems and then do an accounting exercise afterwards. Because there's no other way of doing it. It's not it's an accountancy exercise you have to do. This is not an accountancy problem, it's a systems problem. So not avoiding the question. I mean, there's people who do calculations on wind integration costs and they say it's $4 or $5 a megawatt hour. I think they're reasonably good guesses, but you will not find anyone saying that their methodology is not without flaw. So PV on rooftops in Southern California do have some impacts on the distribution system. They do have additional costs, but they do have benefits. I would not like to say whether it's higher or lower or whatever. Look, it's a policy issue. Do you want to have renewables or not? If you do, there's a cost. Get on and do it. I mean, does everybody know the true cost? I mean, does the United States know how much a war is going to cost it every time it goes into it? No. But it still does it. So, you go into things and you make big decisions. I mean, when GE takes over a company or somewhere, buys some company, does it know if it's going to make a profit or not? That's called leadership. People take decisions. You can't know everything in advance. Do you know when you get married, is it all going to work out? You don't. So you've got to make decisions. So, you can do as much analysis. There's a paralysis by analysis, isn't it? You can do too much of it. You just got to look at something and make a decision. But there's no doubt about it, if somebody comes to me and says, I can give you an idea if the costs are going to be, I can give you a sense, that solution is going to be more costly than that. That's too much PV in that part of the system. So good engineering judgment can probably give you good answers to it. The exact number, it's back to the story about the metric. I want to know exactly how many dollars it's going to cost. It's very difficult to do. Quantifying flexibility and quantifying the cost of integration are two similar problems. Extraordinarily difficult to do. Somebody has to make a decision and get on with it.
Okay, how about Kareem, and then we'll move up here, yeah.
I want to make a comment. I'm interested in hearing your thoughts about it. Specifically, when you said that for the demand response, there's not a lot of revenue for the consumers. And just to spice it up things a little bit, I might push back a little bit on that and say that's because the current business models don't favor the benefits to go to the consumers. They favor the benefits to go to the distributors and to the utilities where you're having very huge margins. So if you change that business model and you give the consumer more control and more access to the grid, you might increase the margin of revenues that they're having.
Oh yeah, I mean, and again, it's back to my point. It's a systems question. It's very complicated. There's many different aspects to it. I still think, though, if you do the engineering analysis and leave out the business model part of it, and you take demand side as a resource and optimize it and run it, there's still not a lot of money on the table. So if you forget about the exact details of the business model, there's just not an awful lot of money on the table. I know, for example, if you take an example of it, in Ireland we have a capacity market. So we pay people for capacity. Now, in that market, there's people who have built a business on it. One of my ex-students has a business. He's 70 megawatts of demand side. He's making a living out of it. Some markets don't have a capacity market. Now, that's a case whereby in one market I can make money, but in another market in another jurisdiction there's no market, so you can't make money. I think if the markets are correct, and capacity markets I think are a valid thing to have. I don't know, do they have a capacity market in California? Do you?
I don't think so.
No, okay, so here you don't have a capacity market. So his business model wouldn't work here, but yet he does bring value to the system, but he can't get paid for it. So I think, you're right. In certain jurisdictions, it is regulations and the details of the rules at the time that are negative towards demand side. I agree with you. But if you do pure engineering analysis on it, you also find there's not an awful lot of money there. There just isn't. You do all the work you can. The simple fact of the matter is the amount of money available for these services is not colossal. It's quite small. And the reason is because your electricity bill is too low. Now, if you increase your electricity bill by 10, then there's plenty of money on the table. So energy is probably too cheap for demand side to participate yet.
Okay, one more question here, and then we're going to wrap up. Yeah.
So I was very intrigued by
There's a lady here, I think, who should be allowed to ask a question.
Okay, we'll have one more after you.
I was intrigued by your slide showing the drop in costs from the forecasting, and I'm curious, as someone living in sunny California, how kind of the solar forecasting is coming along, and it seems like intuitively we might have a more experience with that since we've been predicting how the sky's going to look the next day for quite a while, not necessarily the wind speeds. Do you have any sense of solar?
Solar forecasting is not as well developed as wind forecasting because the technology is only starting to be developed and it's at scale. As my understanding is that they're pretty good at it. In many ways, solar is easier to predict. Why? Because during the night there's none. And during the day there's some. But that's a big. If you do the statistics on it, it's a big issue. So solar actually in many ways can be more easy to predict. But at the same time, it does have a certain amount of error associated with it. I would suspect it's more easy to predict in general. But I think in a very cloudy environment like Ireland, it's not that difficult to predict because clouds can have a huge impact on it. I think some of the issues about solar have to do with clouds and clouds passing over large arrays. And that can bring pretty dramatic changes over very short periods of time. But I'm no expert in it, but I would suspect that it's similar to wind technology. It's been developed, it's getting better. But it's a very important technology. And if you get it right, the benefits are colossal. They really are. They're huge. If you look at the numbers, you just do back calculate some of those numbers. Really good forecasting at very high penetration levels can save 5-6% of 10, 20, 30 gigawatts of wind. It's a lot of energy, it's a lot of money. Okay. But perfect forecasting is impossible, so just be careful. There is a limit to what you can do.
Okay, one more, the last question.
Yes, you have a carbon tax in Ireland, I believe, and I was wondering how that is affecting the demand for renewables.
Affecting the demand? Well, renewables are mandated under EU targets. So we have to hit a target of 40% by 2020. So it's
the carbon tax would make, I think the populace would rise up and say, hey, this is too expensive, we want renewables.
Oh, the carbon tax?
The carbon tax.
Yeah, but okay, so I'm not an expert in the carbon tax in Ireland. The carbon tax in Ireland is there on fuel and it's there in terms of consumption. So people, when they go out and buy fuel for their cars or whatever, they're paying extra, right? In terms of installing renewables on the grid, it's not driven by carbon tax. It's driven by our requirement to meet a target, 20-20-20 targets, 20% energy efficiency, 20% of all energy from renewables, and 20% reduction in carbon. And apparently there's penalties to do with that. So it's not driven by, the carbon tax is not causing this all to be built. It's us trying to meet our EU targets that's causing it all to be built. But I'll say one thing, there is a uniformity of thinking inside Ireland and Europe. Pretty much in Europe, the governments, the industry, and the populace want to do this. And that's important. That's human flexibility, people want to actually do something. I have another slide that shows a man with his head in the sand, but I won't show that.
Okay, all right, well, thank you so much.
Okay,
That was good.
For more, please visit us at stanford.edu.